about the cell point accounted for differential privacy.
Thank you so much. Thank you all for coming. Yeah, so this is joint work with all of these fine folks, most of whom are in the room. I guess Shahab is on Zoom and Faye's not here, but everybody else is around. Okay, so as I am in my heart a true information theorist, I am contractually obligated to start my talk with this guy. So I want to take inspiration from Shannon in a specific way, which is, so what did Shannon do when he was looking at the noisy channel problem? We started with a channel model given by this conditional distribution, and he came up with this thing that we call the channel capacity, right? And the channel capacity is great because, first of all, it has this really specific operational meaning, right? It's asymptotically the number of bits per channel use that you can send across the channel. But the other nice thing about it is that it's one number, right? It's one number that tells you something really important about the channel. And so there's a sense in which once you have this sort of single statistic, you can go back and think about what the channel should be, right? And it's like once you know that capacity is what you want to have, then you can go and think about how to like invest in your channel. You know, how should you change your channel to make it better? So there's a sort of coupling here, and the coupling is allowed by the fact that this is like a relatively simple thing. Right? So I want to make that analogy with these two problems in differential privacy. So one of them is mechanism design. This is like, what kind of noise should we add? And this is, in a way, it's sort of analogous to the channel model, right? And here we have even more control because we basically get to make up the channel, right? We can add whatever noise we want to. And the other problem is accounting. So of course, Ilya talked about this, and also Shahab and Mario. And this is like, you know, given an algorithm, what is how much privacy do you get? And so I want to say this is kind of like the channel capacity, right? It's some way of extracting information from the noise distribution and say, okay, like how good is your algorithm? Right? So there's lots of work on both of these problems. I'm sure I'm failing to list things here. But I want to kind of make this point that these things are sort of inherently coupled. Okay, so I think by now, I probably don't need to spend too much time on this definition, but I do want to, I was just observing that I think the talks in the morning, we've coordinated to make sure that our notations are all slightly different. So I believe that a mechanism is a conditional distribution, not a function, but we can argue about that later. But you know, this is the same old definition of epsilon delta dp that I'm sure you all know by now. So yeah, so you can, I sort of think about it as this way, like, you know, you can have a specific epsilon and delta pair that you're interested in, but really for a given mechanism, there's some kind of continuum of epsilon delta pairs, which you might plot like this, where here's epsilon and delta, maybe a log scale, some curve that looks like this. You'll see some actual curves later on in the talk. Okay, so there's lots of equivalent ways you can write this. This is actually essentially the same as the hockey stick divergence that Shahab and Mario talked about. So here it's equivalent to say a mechanism is epsilon delta dp if it satisfies this condition, where we have this sort of expectation involving this variable L. So L is what we call the privacy loss random variable, and it's essentially log of the density between the mechanism for two neighboring data sets. Okay. So this expectation quantity is kind of the key way of extracting delta for at least for a given epsilon. So I'm going to call this thing delta L of epsilon, and it'll show up a bunch of times in the talk. Okay, so in order to get into this, I want to sort of make a distinction between non-adaptive mechanisms and adaptive mechanisms. So with a non-adaptive mechanism, what you're doing is you have some data set, and you apply a bunch of sort of separate mechanisms over time. So this is like each one is a different composition of your privacy, and each one is sort of uncoupled to the other ones, right? So when you apply the second mechanism, it doesn't depend on the output of the first one. So this is non-adaptive because you don't use that information. And you can see that if you have non-adaptive mechanisms, and the privacy loss random variable is going to decompose into a sum where each of these things is the variable corresponding to one of the mechanisms, and they're all independent. So when you have non-adaptive mechanisms, it's easier to deal with because everything's independent. On the other hand, if you have an adaptive mechanism where when you apply your second mechanism, you are using what came out of the first one, and the third one depends on the first two, and so forth. So obviously, this is the more practical regime if you're training a machine learning model or something, and each one of these things is calculating a gradient and then adding noise to it. The gradient depends on where you are, which depends on the previous outputs. So really, practically, a very useful regime, at least, is adaptive. And when you have adaptive mechanisms, the privacy loss random variable isn't going to be independent in the same way. But it turns out you can kind of assume it's independent. So there's this nice result by Dong et al., which I'm kind of vaguely summarizing here, which is that and what it says is that even if you have adaptive mechanisms, there's a way to come up with independent privacy loss random variables such that you essentially can treat it as if they're non-adaptive. So you have the same delta L function that I showed in the previous slide with the expectation of L, where L is a sum of these independent. So even though with the adaptive mechanisms, your individual privacy loss variables aren't independent, let's just assume that they are. And we can use this result to kind of get. As far as I know, every privacy accountant is essentially doing a version of this. So if you want to really deal with the dependence between these variables, it's very difficult because you have to understand kind of how exactly the previous outputs are being used in each step. So we're not doing that. We're just assuming everything's independent. Okay. So as I said, there's lots of privacy accountants. I've kind of divided them into two groups, which I'm calling order 1 methods and little omega 1 methods. So what I mean is the dependence on the number of compositions. So this stuff, it's independent of the number of compositions. So for any number of compositions, it's still sort of a constant. The amount of time it takes to compute this thing doesn't change. Whereas here, as the number of compositions increases, the amount of time it takes to compute it also increases. So over here, we have stuff like Rennie DP, Moments Accountant, also Gaussian DP. I'll talk more about that later. And then over here, there's things based on the FFT, also another algorithm called Connect the Dots. And so I guess I want to say that I'm really focusing over here. And again, this goes back to this inspiration from Shannon that if you have an order 1 method, that somehow it has to be based on just maybe 1 or 2 numbers that you extract out of your mechanism that tell you the key things about how that mechanism performs. And that ability to extract insight is kind of what's going to connect it to the mechanism design problem. Oh, I should say, so this talk is really, the main focus of this talk is epsilon delta dp. So Rennie dp will kind of come up, but it's really, everything is sort of in service of epsilon delta, at least for the purpose of this talk. Okay, so let me tell you about some of these things. So I'm going to start with Gaussian differential privacy. And the inside of Gaussian differential privacy, at least in my mind, is, okay, so you have this privacy loss variable, which is the sum of a bunch of independent things. So the central limit theorem tells you that this thing is going to be roughly Gaussian. So if you can write the delta as this expectation of this function of L, well, then you're going to get a pretty good approximation by just replacing L by a Gaussian. So here N is a Gaussian random variable with the same expectation and variance as L. This is kind of what the central limit theorem would tell you to do, and like this thing is fairly easy to compute. So this is like a pretty good approximation for the privacy that you get. We can also show, as far as I know, this exact thing hasn't been proven previous to that. So here, this is epsilon for a given delta as opposed to delta for a given epsilon. And so this is saying that as in the limit as the number of compositions goes to infinity, epsilon looks like the expected value of the privacy loss variable and some additional term having to do with the variance. And so this is like the inverse Gaussian CDF. So this is the Gaussian approximation is coming up in here. So if you look at these things in terms of the number of compositions, so n is the number of compositions, this thing is order n, and this thing is order root n. So the kind of most significant element of this is this first term, right? So if you're doing a whole bunch of compositions, so if you're training your machine learning algorithm with tens of thousands of iterations or more, the n is gigantic. So by far the dominating thing is that first term. And so again, if you want to connect this back to how should we design the mechanism, so sort of to first order, we should minimize just this expectation of L. And in fact, the expectation of L is just the KL divergence between the two output distributions. So in some sense, this is like a capacity, if you like, of the privacy problem, because as the n in the sort of asymptotic little mini composition regime, that's the sort of dominating term. Okay. So what we can do is we can optimize for that KL divergence. Okay. So I'm going to assume that we're in a regime where each individual composition looks like this. So we have our data set. We apply some function to it, which is like, it could be like calculating the gradient. And then we add some noise. So here we're assuming this noise is kind of independent of everything else. So it could be Gaussian noise, but maybe Gaussian isn't the right thing. Right. And so you can sort of work out, okay, what for given a noise, the KL divergence that you want looks like this. So if we want to find the best noise, we should minimize that thing subject to maybe some cost constraint. So this cost constraint could be, for example, quadratic cost. You can plug in other things there as well. So the first time I saw this optimization problem, I thought it looked a lot like a rate distortion kind of problem from information theory. So I assumed that the answer would be Gaussian. But it's actually not. It's sort of different in an important way because this isn't the mutual information. This is a KL divergence between two distributions, which are kind of shifted by some sensitivity parameter. So it seems like even for quadratic cost, this has no closed form solution, as far as we were able to come up with. And it's an infinite dimensional optimization problem, although it is convex. So we were able to kind of solve it numerically just by applying a sort of quantization scheme. And what we find is that the sort of solution to this has this really funky shape. Right? Question. Oh, so we need something here, because if you try to minimize this thing subject to nothing, you can get infinite privacy but terrible utility. So we have some cost function, which is sort of a proxy for a utility. And so for this shape, I'm assuming a quadratic cost. So we solve this thing and we get this funky shape, which because some of us are from Arizona, we thought it looked like a cactus. So we call this the Cactus Mechanism. And it's sort of, in this sense, sort of asymptotically optimal. This is the distribution for scalar queries. So this is a scalar distribution. So it's definitely not Gaussian, which means it's doing better than Gaussian, at least in terms of this KL divergence. So the only problem with this is that this is all derived from this Gaussian approximation. And in fact, this thing is only derived from the first term in the Gaussian approximation. We didn't even use the variance, right? And the Gaussian approximation is pretty good, but it can be inaccurate if you're sort of in the moderate composition regime. And the reason for this is because there are large deviation effects that are important, right? Delta is going to be really small. So you're in this regime where you're interested in probabilities like way on the tail of the distribution, which is the large deviation area. So the Gaussian, the sort of the central limit theorem doesn't talk about large deviation. So we need a sort of slightly different tool to get a more accurate thing. And what's going to become the saddle point account is a way of doing that. It's a way of kind of tweaking this Gaussian approximation a little bit so that we get kind of good effects for the large deviation regime as well as a sort of Gaussian approximation. So what we're going to do is exponential tilting. So this is sort of a very simple idea. You have some random variable L with some PDF, and we're going to come up with a tilted version of that variable, which I'm calling L tilde. We have this tilting parameter T, where you just take the PDF, multiply it by an exponential in T, and then find a constant to make sure that it's normalized. So there's some picture like this. So like the yellow thing is the original distribution. You apply this tilting and you just sort of change the shape a little bit. You can think about this as like important sampling. You can write this like the normalizing constant in terms of the cumulant generating function of your variable L. And when you do this, you can do all sorts of tricks. So for example, if you have a bunch of, if L is a sum of a bunch of things that are independent, then the tilted version is a sum of a bunch of the same tilting applied to each individual variable, and these are again independent, right? Also, any expectation of L can be rewritten in terms of the tilted variable. It's very simple, just to kind of put in an exponential and take it out, and then you have this very simple form. So we can apply this to the privacy calculation. So again, here's our delta L function, which is this expectation of a function of L. And so you just apply this to get something in terms of the tilting variable. It looks like this. Again, here's this cumulant generating function popping out, and now it's an expectation in L tilde, but there's just this additional exponential term in T. So you can do one more movement where I've just sort of pulled out another e to the minus T epsilon, and the e to the T epsilon showed up in there. And so this is an equivalent way of saying it. Now this expectation here, it's pretty easy to see this thing is always less than or equal to 1, because this sort of, so this positive part thing is only non-zero when L tilde is greater than epsilon. And so if L tilde is greater than epsilon, then this term is less than 1, and so is this term. So the whole thing is always less than 1. And if you just do that straight bound of just like, okay, let's upper bound this thing by 1, this gives you a privacy account. This is in fact the moments account. So this is kind of, I mean, the first one, or an early privacy account, which is very good. And it looks like this. You just take this upper bound to be 1. And then you can also minimize over T to find the sort of the best tilting parameter. Right? So you solve this by the derivative of the cumulant generating function should be 0, should be epsilon. So I should say the cumulant generating function is essentially the same as the Renyi divergence, right? T is like, I think T is like alpha plus 1, or essentially the same. So this is more or less what Ilya was talking about this morning. Okay, but you know, taking this to be less than or equal to 1 is a fairly crude bound. We can do a little better. So if we just combine these two ideas, so we first start with this formula for delta in terms of this tilted variable L, and let's just replace L with a Gaussian with the same expectation of variance. Like I said, so now we have N tilde, which has the same, which is the Gaussian, same expectation and variance as L tilde. And these, by the way, these numbers you can very easily get also from the cumulant generating function for the privacy loss variable. So this is sort of combining both the kind of large deviation effect via the exponential tilting, as well as this sort of central limit kind of approximation. So this is what I'm calling saddle point number 1. So this is the first of these saddle point quantities. So there's another one coming up. This is called, we call this SPCLT, central limit theorem. And in fact, we can prove a hard bound on this. So a hard sort of error bound. So this is a bound on the difference between the sort of the true value of delta and this saddle point approximation. It's given by this complicated formula that I'm not going to talk about. We can prove this via Berry-Essing theorem. And by the way, the reason this is called the saddle point approximation should not be clear yet. I'll explain that in a minute. Okay, so this is great, and this is going to sort of be a correction on the moments accountant, if you like. So the only thing that's kind of weird here is like, okay, so how should we choose T? T is this tilting parameter. So you can kind of, you know, this bound applies for any T. So you can just make up how you choose T. But it turns out there's a kind of mathematically inspired specific way to choose T that seems to be pretty good. So let me try to tell you about that. So here's a different way of thinking about this situation. This is going to be a kind of Fourier version of this analysis. So this is the Percival-Plantrel identity, which says if you have some integral of the product of two functions, you can replace them with the Fourier transforms and you get the same value. It's very, very, very basic idea. Okay, so we can apply that idea to this expectation. So this is just rewriting the expectation as an integral. Let's do the exponential tilting thing. So all that means is I multiply by e to the tx and then e to the minus tx. Right. And then these are my two functions. So the stuff over here is going to be like f, and the stuff over here is going to be like g. And I apply Parseval-Plancherel, and I get this. So this stuff is essentially the Fourier transform of this. And then this thing involving the cumulant generating function evaluated at this complex argument is the cumulant generating function of this. So the tilting parameter t is in there still. Okay. I can write it in a slightly different way where I take an integral over z, where z is this complex number. And basically what's happening is I'm integrating in the complex plane along this line, right? And the exact line I pick is based on t. So what's interesting here is that the value of this integral actually doesn't depend on t. It doesn't matter exactly what trajectory you take in the complex plane, which is kind of something we should not be surprised by from complex analysis. So there's a sort of equivalence between the trajectory you're taking in the complex plane and this tilting parameter. Okay, and we can also rewrite this by kind of shoving everything up in the exponent, where we have this just e to the f epsilon, where f epsilon has all these terms in it. So now we've kind of converted this problem of calculating delta into calculating this complex integral. Now there's a trick that's used all the time in statistics and even physics, where it's called the method of steepest descent, which can be used to approximate integrals like this. So how does that work? Okay, so we have this integral, it's a complex integral. So what we do is we find this thing called the saddle point. The saddle point is a real number t naught that minimizes this function up in the exponent. So you can very quickly determine this function is convex and its derivative is given by this thing. So you just solve this equation to find the saddle point t naught. This is actually very similar to the moment's accountant condition, which was just KL prime equals epsilon. So there's just these sort of extra terms showing up here. Why am I calling this saddle point? Because it really is a saddle point. So if you think about this f epsilon thing in the complex plane, along the real axis, it's kind of a minimum, and along the imaginary axis, it's a maximum. So the saddle point is this point here. So because it is the t naught that minimizes this thing. And then what you can do is you can just apply a second order Taylor approximation to f epsilon around this saddle point. And then you can evaluate this integral and you end up with this term like this. So this thing I'm calling saddle point number 2. So this is the second kind of approximation based on this idea. So this one is MSD for method of steepest descent. And it has some flavor of Gaussianity when you're taking the second order Taylor expansion, right? You have a kind of Gaussian looking integral here. Okay, so now we have these two approximations based on versions of the saddle point. We had the first one I talked about, SPCLT, and the second one is SPMSD, which look kind of different, but actually they have more in common than you might think. First of all, they each have a t in them. And what we're going to do is just use the saddle point value for t in both of them. We can also show is they have a connection theoretically, which looks like this. So the CLT is upper bounded by this, which looks a lot like the MSD one, but not quite, because here we have k instead of f in the denominator. But like f is mostly driven by k, so they're not too different. What we also see empirically is that these two approximations are usually very close. They have some pluses and minuses. So like with this one, we were able to prove this sort of hard error bound, whereas with this one we weren't. But it's also sort of simpler as an expression. The other thing about this method is that you can actually get even more accurate approximations. So if you kind of take more and more terms in your Taylor expansion, you can get a sequence of approximations that get more and more accurate, but get also some more complicated, which I'm not going to write them out. Okay, so here's some numerical results. So this is for subsample Gaussian mechanism. Okay, so there's a bunch of lines here. So the dashed white lines are the bounds from the SPCLT. So this is the error bound plus or minus. The red is the moment's accountant. This yellow one is PRV, which is the Gopi et al. Version of the FFT accountant. And then this one is the connect the dots algorithm. So for this, so again, and here's like this is epsilon and delta, right? So okay, so for the, I guess the SPCLT and the PRV accountants have an upper and a lower bound, right? So maybe the upper bound is the more useful one, but they do also give you a lower bound. The other thing about actually both of these two accountants, which are kind of numerical accountants, is you can give them a desired accuracy, and they will give you, you can make them more accurate just by sort of running it for longer. So we've plotted them for a specific accuracy, and you can see that's why kind of this thing at some point stops being a good approximation, because there's nothing wrong with it. It's just like we only asked for that much accuracy. If you wanted it to be more accurate, you could make it that way. And the same kind of thing for the connect the dots algorithm. I should say that getting these numerical accountants to be super accurate for really small values of delta, like down here in the 10 to the minus 20 range, that seems to be pretty hard, because you start to run into numerical accuracy problems. So one nice thing about the saddle point is that it basically gives you this like really far large deviation regime very easily. Moment's accountant is also doing fine for the same reason. So maybe delta equals 10 to the minus 20 is an impractical regime, but at least in principle we can get there. Here's another plot showing how well these things do. So this is for a fixed mechanism and a fixed delta, where we're varying the number of compositions, and then I'm plotting relative error in epsilon. So we were able to compute a kind of ground truth epsilon, and this is the relative error. Okay. So what you see is both the sort of Gaussian approximation and Moment's accountant are not doing great. The SPCLT bounds are better, but what's actually interesting is that the SPCLT approximation itself, so this is the kind of the middle of the bounds, is actually way better than the bounds are indicating. So it seems like the bounds are pretty loose. This error bound is pretty loose. The other thing, so I have 3 versions of the SPMSD. I said you can get kind of more and more accurate approximations. So k equals 1, 2, 3 are sort of 3 versions of this Taylor expansion. So that's k equals 1. So you see it's kind of roughly similar to the CLT approximation. K equals 2 is actually also very similar. K equals 3 gets dramatically better. That's the best one here. So in terms of just pure accuracy, this one's super good. Okay, so in the last few minutes, I want to get back to mechanisms just a little bit. So I argued that if you have one of these order 1 accountants, it can give you insight on the best mechanism. So let's sort of get back to that. Okay, so again, we're in this setup where we want to find the best noise. And in principle, you can write down this optimization problem where you'd like to minimize some cost for the noise subject to a constraint on the actual saddle point, right? So this is the saddle point number. Here, I guess I put the cost in the objective instead of the constraint, but it doesn't really matter, right? This is a very similar kind of idea to what came of the Cactus mechanism. So this is a little harder because this is now a non-convex problem, because the CLT expression is sort of more complex. It's not necessarily convex. We would also like to solve this for a multi-dimensional noise. So if you're training a machine learning model or something, you have to add not just a scalar, but some kind of vector noise. So we're going to assume that our noise distribution is rotationally symmetric. And again, we can sort of apply some kind of quantization and then just do gradient descent and try to optimize this mechanism. And the gradients are kind of easy-ish to compute. And the reason that they are is, again, because this thing only depends on a few numbers, right? So this is going back to this insight I'm trying to get from Shannon, that like, because it's only a few numbers, you only need to worry about those numbers in terms of your mechanism. So here's what some of this saddle point optimized mechanism look like. So here, optimizing for these parameters, and what you can see is the nice thing about the saddle point optimization is that you can dial in exactly what you're interested in. So this is like, you pick your epsilon delta, you pick your number of compositions, you pick your subsampling rate, and it'll in principle give you back a mechanism. So this is the distribution of just the radius of the distribution. So the yellow is the optimized one, the red is just Gaussian. You can see they're not that different, but this is sort of reshaping this thing a little bit. And then I guess this is with the 17-dimensional noise. The reason we picked 17-dimensional is because we're going to apply this to train a simple machine learning model. So this is on the new adult data set. We're just doing logistic regression, so it has 17 parameters. So we're going to add this noise. And we're basically doing DPSGD, except with one of two different noise distributions. Here, delta is always 10 to the minus 5. And what I'm plotting is epsilon versus accuracy. So there's, for each of these two noises, we ran it for a certain number of compositions. And the more compositions you go, the higher epsilon gets, but also the accuracy gets better. Okay. And so these two, we picked the Gaussian to have the same variance per dimension as the SPA optimized ones. They have the same variance. And you can see you get, what's really better about the optimized one is it's a little better, its privacy is better. It's not just that its accuracy is better. It's mostly better because the privacy is better, not because the accuracy is better. But you see, for a given desired level of accuracy, you can get like maybe 1 epsilon or 0.8 epsilon. So in principle, this seems like it could be good. Okay, so let me just conclude. So again, the kind of main point I'm trying to make is that this is coupling between mechanism design and privacy accounting. I talked about the saddle point accountant, which is simple and accurate even for very small epsilon. And then you can kind of use this insight to optimize mechanisms either from KL divergence, which was this thing called the Cactus Mechanism, or from the saddle point itself. And the optimized mechanisms seem to outperform Gaussian, at least in these preliminary experiments. And I should emphasize that that last slide this is very much ongoing work. So yeah, we're still trying to understand exactly how much better you can get if you optimize a mechanism. Okay, so there's a cactus and there's a saddle and there's some archive papers. So thanks very much.
Questions?
One of the is not and it sure made sense to me why you might prefer to add noise like 7 noise rather than 6 noise. Do you have an intuition on this?
Yeah, so this is a great question. And to answer the question by agreeing with you, so that there is in addition to it being weird, it's not a good idea from a different reason, which is that the accounting is actually really hard because you don't know exactly what shift is the worst case shift. But the way, if you remember back when I talked about this Cactus optimization problem, it does consider that. It maximizes overall possible shifts. So it's sort of accounting for that. And in that sense, we know that this non-monotonic mechanism is going to beat any monotonic mechanism if you could account for it, which is the big if. But okay, so your real question is, why is it not monotonic? And the answer is, I have no idea. This is what the optimization problem gave us. I guess, why, maybe we'll turn it around. Why should it be optimal, right? Like, or why should it be monotonic?
So did you have did you empirically or theoretically have a statement that it's better than any monotonic distribution?
We do know that theoretically, because you can, because you can, if you make the quantization in bins kind of small enough, you can get arbitrarily close to the true optimal, and you can optimize without a monotonicity constraint or with, and you see this again. So you can also optimize with the monotonicity constraint, in which case it'll be monotonic, but it's still kind of funky looking. Yeah, so I wish I had a better answer for like why it is, but it just seems to be a.
So there is some kind of computation cost associated with it, right? I mean, comparing like SPA to a Gaussian is such simple to run, and I mean, how does it scale?
Yeah, so I think when it comes to when you're actually training it, so once you've already found the mechanism, yeah, it's a little harder to sample from one of these things, but I don't think that's a big deal. I don't think the computational time of training a model is dominated by generating the distribution, right? So even this is not going to take very long. The thing that does take a while is solving the optimization problem. So, and if you really, as I said, you could kind of dial in exactly what you want to do. And then the downside of that is that every time you want to run this with different hyperparameters, you have to optimize it. But I guess I would argue that if your ultimate goal is privacy rather than just computational efficiency, right? When you're training a machine learning model without privacy, then what you care about is you want to solve it quickly. You want to get a good solution quickly. But if you care about privacy, it seems to me you should be willing to give up some computational efficiency for that. So if you can get 1 epsilon better for the same accuracy, but you spend 5 minutes running an optimization problem.
But again, you lose the closed form. You don't have any closed form solutions anymore, right? Which is
no, yeah. Yeah, but we have some other work on a different, which would be a whole other talk that has some closed form things. But yeah, all the stuff I talked about here is sort of entirely numeric.
So maybe actually a little related in this point, how easy is it to sample? I mean, they look like Gaussian, but they're not Gaussian is what you're saying.
Yeah.
Are you sure you can sample from them secure, like in a way that really satisfies DP in a cryptographically secure fashion or not?
I think so. I mean, if you believe that any random number that's coming out of a computer is random, then which maybe it isn't. But it's not that hard. As I said, it's harder than a Gaussian. But I mean, how does a computer sample from a Gaussian? Does anybody know? Like that's been optimized because everybody wants Gaussians, and so there are ways you could make this thing more efficient. But I mean, I think what you're really asking is, can you be sure you're sampling from the right distribution? And you have to be careful about that to a certain extent. But you have a bunch of bins, and there's a probability of each bin, and within each bin it's a continuous distribution within the bin. So you want to uniformly choose a radius or something within that bin. But as long as you do that, I think you're fine. Yep.
So the Cactus, do you have any sense of how much better it is than a Gaussian? You didn't show a comparison of the Cactus against the.
Yeah. So yeah, I don't have that plot. So I don't have a good theoretical notion of it. One thing that's interesting is as the noise variance gets bigger, the gap between them gets smaller. So this is actually another line of work that I don't have time to talk about. That essentially as the noise variance goes to infinity, they become the same. So it's much better at small variance, and it gets less so at higher variance. But that's not really an answer to your question.
Okay, folks, I think we can take the remaining questions offline. Let's thank all the speakers.